Karl Müller has had a distinguished career in Vienna, Austria. He was head of the Department of Sociology and Political Science at the Institute for Advanced Study in Vienna. Then he was the director of Wisdom, the Vienna Institute for Social Documentation and Methodology. That was a social science data archive. Now he's the director of a Center for the New Cybernetics. It's a great pleasure to introduce Karl Müller.
Hello, and thank you, Najib, for taking the risk of inviting me again. And this time I thought there's so much talk about innovation, and I was supposed to talk something about innovation in science, but I wanted to change my talk a little bit by focusing on innovation and what's behind all of us in times like these, and what I wanted to focus on initially, and that's not what this was also due to the presentations yesterday and today. I want to show you 4 great transformations in science and society, which are ongoing and which have taken together a remarkable characteristic, and I will take you now on to this tour through 4 great transformations. I start with what Hans Bichler already told us, and start with Joseph Schumpeter and industrial revolutions. And here I want to turn to a very specific focus of these Schumpeterian revolutions, and that's in his book on business cycles. Basically, he says, so far we have 5 of these industrial revolutions. It started with textile industry and steam engine at the beginning of what we are also classify as industrial revolution, end of 18th century. Then it was railroads from the middle of the 19th century, then electrochemical industry at the turn of from the 19th to the 20th century, automobiles were after 1945, and then information and communication technology. And if one, in the Schumpeter clock of periodizations, this last basic innovation started around the 1990s. And so we are amidst this Schumpeter, within the Schumpeter clock, we are amidst this revolution in information and communication technologies. That's great transformation number 1. That's great transformation number 2, and this is with respect to the science system. And here I want to refer to a very, very interesting book by Nicholas Rescher on the scientific growth and development. And he had a very interesting idea of characterizing the growth of knowledge, not in some sort of linear way that today we know something, tomorrow more, and in 2 weeks much more, but in a cyclical manner. The evolution of knowledge throughout the 16th, from the 16th century onward, was an up and down in terms of knowledge horizons. There were periods in science when the knowledge horizons were almost closed. So it was a state of some sort of almost perfect knowledge. It was, for example, around 1900 or 1895 when Max Planck wanted to study physics. And he was told, please don't study physics. Basically everything which physics had to invent was invented. Don't do it. But then from 5 years later and so on, there was this revolution in physics. And in this metaphor of Russia, then the knowledge horizons moved down, and the knowledge horizons opened up. And the period from 1940 to 1960 was, according to Russia, and I think there's very much to it, was the most open in terms of knowledge horizons. Think of our conference. It's systemics, informatics, cybernetics. All three fields were founded in the years between 1940 and 1960. So there was a new wave of interdisciplinary disciplines, cybernetics, system science, information science, and we are still working on this. And what I and others made out of this Russia scheme and saying that we are currently experiencing a big change within the science system from something which I called Science 1. This was classical science from the age of Copernicus, Galilei, Newton until 1900, 1940, 50, to Science 2. And it's a new architecture of science, and in the last lectures I presented you some of the main dimensional changes and so on, but basically we are currently undergoing this revolution in science, and there are two principal components. We have a rapid rise in complexity levels in science, and what I will argue today, also reflexivity levels. And we have all sorts of changes within the science production processes. We have the change from what I call from id science to bit science, so the material workplace changes to a digital workplace, the knowledge base changes into a digital knowledge base. So that's the big, great transformation number 2, great transformation in science. But that's not all. We come to a third great transformation, and this is an invitation to you. So far we looked at science and economics, and the Schumpeter clock started with the first industrial revolution. The science clock started in around the 15th or 16th century, but now we have a very long clock, co-evolutionary clock, beginning of life. So it's a billion, several billion years, and in terms of co-evolution, it's a change between certain species and their knowledge base, and the way this knowledge base is encoded. And I don't want to go into the details here, but basically, there's now what I call Piaget Societies. And Piaget Societies, these were all human societies which had scriptures, and which developed some sort of symbolic codes. And we have a very large number of symbolic codes, be it alphabetic codes, mathematical notations, music notations, and so on. So these are the Piaget Societies. They had scriptures. They had a knowledge base. A knowledge base in Piaget Societies by the big libraries and so on. This was the Piaget Societies. But these Piaget Societies are now transformed into what I would suggest as into Turing societies. There's a new, we are still here, but there's a new type of species, Turing creatures, Turing systems, Turing machines, Turing networks, all running on a machine code, new code. And it's very, very interesting to see that now the libraries and the books and the old knowledge bases are transformed more and more in this digital knowledge bases. And so there's a huge transformation going on, which I would call this transformation from Piaget Societies to Turing Societies. That's great transformation number 3, and we are amidst it. But there's a fourth great transformation. And here we'll come back to the notion of innovations again. And Schumpeter had this vision of these big innovations as cycles. So there was an upward cycle and then a downswing and so on. And I would suggest here a different way of conceptualizing it, that innovations are distributed in a in a power law fashion. Power law fashion means, or power law distribution means, that's a distribution where you have a very large number of very small things and a very small number of very large things. So in terms of innovations, you have a very small number of very big innovations, and you have an incredibly large number of very small innovations. And this way of seeing innovations along such a power law distribution, I think that provides some interesting examples. And it's interesting in this, due to all this literature on complexity science and so on, to see that these power law distributions that's the mode of self-organization in a lot of societal and natural systems. So for example, the financial system has been organized in a power law fashion. We have a very large number of very small variations on financial markets, and we have a very small number of very big crashes throughout the last decades and now. Wealth is distributed in a power law fashion. Income, scientific quotations, that's a process we all produce. But there's a very large number of quotations or books or articles and so on which get never quoted. And there's a very small number of articles and books which get quoted over and over and over. So it follows this power law distribution. Scientific breakthroughs. We have, like innovations, we have very few big breakthroughs and a very large number of very small scientific innovations. Word frequencies, migration processes, and so on. They all follow this. These are societal processes which follow this, which exhibit such a power law distribution. And we have earthquakes and a lot of things in the natural world organized in a power law fashion as well. So we have a very small number of very big earthquakes and a huge number of marginal variations. We have forest fires, ecosystems, and so on. Now I come to this dynamics of this risk, of these risk processes, risk in terms of rare incidents, strong consequence. Risk, and it has some connotations with risk, with K, as we normally understand. So these societal and natural risk processes, in terms of their long-term dynamics, they have a stage 1 where societies were distributed around the world, but locally no or practically no connections between them, and natural risk processes, and they were somehow independent. Then there was a stage 2 when societal risk processes became global. And this started out in the 15th century and went until, again in this period, 1940 to 1960, when the economic system has become globalized, truly globalized. You had global actors, multinational firms. The regions of the world were somehow separated and so on. So it was, by that time, we had a global economic system and for example, global science system, global technology system, and so on. But, and now I come to the fourth great transformation, what started around this time, and now it's in full underway. We have now a coupling between these natural and societal risk processes. The global economic system produces pollutions and so on, which interacts with risk processes in the atmosphere, and the two risk mechanisms couple, begin to interact, and this type of, and this is, for me, one of the reasons why from this period, 1940 to 60 onward, should be qualified as Anthropocene. There's a human interference with the atmosphere and the phenomenon of climate change. This was great transformation number 4. Taking all these 4 transformations together, and this, I would say that no generation in human history was confronted with such a massive accumulation of great transformations simultaneously, because they happen in the period from 1940, 1960 onward simultaneously. A revolution in information infrastructures, a science revolution, a co-evolutionary transition with Turing creatures, Turing networks, digital knowledge base, and a geological transition, the Anthropocene, due to a coupling of these natural and societal risk processes. So this is something maybe which stands also in the background of all our presentations here. And I would invite you to this perspective that we live in highly turbulent times. Whenever you feel lonely or bored, think of it. You live in very turbulent times. And so this was something which I wanted out of spontaneously tell you, and maybe it's interesting for you. But I come now back to this, what I wanted to do, this science revolution and what I want to do is one special aspect of it, and namely second order science, and what this means in terms of a new potential and new ways of doing science. Here I come now specifically to changes in the science system, and one big change from the period 1950 onwards to 1915 or 16, that we see the emergence of large-scale research infrastructures, and especially in Europe, we can see that there has been now an organized process coordinated by European Strategy Forum on Research Infrastructure, ESFRI, and ESFRI came out now with roadmaps for research infrastructures for all scientific disciplines, whether it's social sciences, technical sciences, mathematics, material sciences, and so on. And these research infrastructures are, of course, integrated through these new information and communication technologies. So that's a big change, these new research infrastructure, and here's an overview of this first roadmap. There's a second change in the science system, and this is a change in terms of reflexivity. Around in the year 76, there was an educational scientist, Gene Glass, who first wrote an article about primary data analysis, or primary, secondary, and meta-analysis of research. And he said, primary data analysis, that's clear, you collect data, analyze them, and write articles. Secondary data analysis, also clear, you take data from someone else, analyze them, and write an article. meta-analysis, and this was the first time that the term meta-analysis came up, 76. Meta-analysis, you take several studies, combine the data and perform new statistical analysis on these data. And in terms of psychological abstracts, for example, prior to Glass' article in 76, no mentioning of meta-analysis anywhere. In 77, there were 2 mentions, 78, 4, and then 84, 63. And from then on, meta-analysis became a very common way of doing things. We have, meanwhile, literature reviews and so on. But what's happening in a self-organized way within the science system is that we have now some sort of a level differentiation of the science system. The first order level is the science system as we know it. So nothing to learn from us with respect to first order science. That's science as we practice it. The zero order level is now the science system of research infrastructures. And this will become a permanent part of doing science. And one can assume that maybe 1/6 or so of all research funding goes into this type of zero-level science. Now, second order, and this is where I want to invite you, second order science is something which goes very far beyond what meta-analysis literature reviews can do, and here we have now just a short, with respect to this functional differentiation, to say what's the function of now this zero order level. First order science is the science for exploring the world. So that's what we continue, and that's still reserved for most of our scientific activities. But zero order science, it has now a catalytic function. It enables, whether it's a big research institute like CERN, they enable new experiments, generate new data. They have this catalytic enabling function for first order science. They provide experimental data, they maintain data, maintain documents and so on, and these are all the tasks for zero order science. And then now to second order. It's come to first order is still the science of exploring the world. But second order science has a reflexive function of first order science. Quality control, higher degrees of robustness, more integration, innovation for the science system, and things like tests of tests, patterns of patterns, studies, generative mechanisms of generative mechanisms, and so on. Now, in terms of academic fields and so on, I think one can make a correspondence principle. Whatever you have in terms of fields, disciplines, and so on, for first order science, you can establish a field on the second order level as well. So you can talk about from first order sociology to second order sociology, from first order psychology, second order psychology, first order management science, second order management science, and so on. Some sort of basic outline of what second order science can do. It operates in principle on all building blocks of first order science, whether they are inputs or outputs. So meta-analysis is more or less on output-based, but it can be also input-based, and it has these two goals of quality control, innovations, and for lack of time, I cannot go into this basic methodology. So again, on all elements of first order science, you can create studies in second order science. For example, here the theoretical concept. Yesterday, I had a lot about quality of life, for example. There are approximately 500 different conceptualizations available on quality of life with different dimensions and so on. a second order study, you would take all 500 conceptualizations, create a new vocabulary, and create something more integrative, which is, of course, not included in one of the 500 questionnaires, and you do some systematic analysis along these lines. You can do this type of second-order study within a small first-order domain or in a large first-order domain. Should tell you something which we did in terms of a narrow second-order study. We made a second-order study of the European Social Survey. This is a big data set which is in existence now from 2001. And so far, 3,000 articles have been produced using data from the ESS. And we created then, in terms of the second-order analysis of the ESS, we created a very in-depth database based on an in-depth analysis of each of the articles, each of the 3,000 articles, and we listed the number of authors, the nationality, which ESS data were used, how many rounds of ESS is reproduced in every 2 years, and so on. So we came up with 40 or 50 different dimensions for each article. And this cannot be done automatically, but one had to read these articles and so on. And the surprising result for us and for others was that by doing this type of analysis, you were able to create an ESS study of ESS studies, which was relevant for a lot of different groups outside the survey research. So if you forget the two first entries, but statisticians received a lot of insights of the need for new methods. For example, although there were 6 rounds of the ESS, 70% of all articles just used a single point of time. And almost no article produced all the data, all points of time. And this is also a lack due to available statistical methods, how to deal with multiple countries, multiple points of time. It was interesting for science policy and science policy analysis because there were one could say something about the relevance of the ESS for methodologies of science, and it's extremely interesting to get an insight also on the on the interests and the theoretical profiles of European social scientists. And it was, for example, very interesting that the ESS had a data set, had a perfect data set for mobility research. And mobility research was very big in the 1960s and 70s, and there were a lot of social science literature on this. Now, and plus, they complained you don't have the right data. We don't have the right data at that time. Now you have the perfect data, but nobody made a mobility analysis with these data. So you get theoretical profiles, dead topics, and things like that. Here's, towards the end of my presentation, Heinz von Förster, who had this vision of a new Copernican revolution in science. I think this is underway along these dimensions of complexity and reflexivity. And I conclude with some small aphorisms. With first-order science as a science of exploring the world, second-order science as the science of reflecting on these explorations, but not reflecting in this in a philosophical sense, but in terms of doing statistical work and analytical work. And there's now a new book coming out from me on post-disciplinary cybernetics as the science of reflecting on these reflections. Thank you for your patience, despite so much novelty.